what we talked about yesterday? So mostly yesterday was a lot of just explanation, and my whole goal was I wanted to sort of justify the process by which we create what we call confidence intervals. And we started out by looking at how to estimate proportions, which are just another name for percentages. And what we came up with is that you could come up with a 95% confidence interval for P, because remember, P is the true proportion, and proportions are just the math way to write percentages. We just use them in decimal form when we operate with them. And so the formula I came up with was, this thing right here. That's what we came up with yesterday, right? Okay, that was the formula we were using. And a confidence interval consists of two things. It consists of the number in the middle of the interval. That's called your point estimate. It's like the one number that you calculate from your sample. If you had to pick a number, that would be the one you'd pick. But this whole thing is what we call our margin of error. And the reason we give ourselves a margin of error is why? Why do we give ourselves a margin of error? Because we don't actually know the truth, and we know that our answer probably isn't the truth, because we just took a sample from the population. So we give ourselves a margin of error. The way that this margin of error was justified, though, is because if you look at the normal distribution, 95% of a normal distribution is within 1.96 standard deviations of the truth, or the mean, and so in this case, we give ourselves a 1.96 standard deviation margin of error, and that formula happens to be the standard deviation of the proportion, and anyway, so that's where it came. And then we did an example yesterday, right? Yes. Okay, so we did the example here for this right here. I don't have it written down, but I can't remember. What did it come out to be? Just can you just give me the interval?
0.3674.
3674 up to
0.4792.
4792, right? So that was our confidence interval that we worked our way through and got down to. So we decided that we could be 95% confident at the true proportion of somewhere between 36.7% and 47.9%. Like that's probably a reasonable range where we would expect the truth to be. So our data isn't useless. We have a range of values, but you might want to adjust. Maybe you would like a tighter range, or maybe you'd like to have higher levels of confidence. And so this formula is flexible. It can allow for other levels of confidence. And so that's why you have this little table down at the bottom of your positive side of your Z table. It helps you really quickly adjust for other confidence levels. So like, for example, let's say, I'll show you how to get one of those. I'm not going to show you how to get all of them. But let's say, for example, that you wanted to increase to like 99% confidence. Okay. All right. So if you wanted to, you go up to like 99% confidence. Well, the way we found that 1.96 yesterday, I don't know if you remember, but what we did is we loaded up our confidence level all in the middle of the normal distribution, right? And then what did we do? The tails then were basically what was left over after the confidence. So that leftover probability, that's what's called our alpha level. So our alpha level is sort of like the error rate. You can think of the alpha level. So I used that Z alpha notation a while ago, but what we're usually talking about as an alpha level or an alpha in statistics is we're talking about our error rate. It's basically the complement of the confidence. So what we do is we took that alpha level and we split it in half. 0.0. So like for 99% confidence, you split it in half, and you have 0.005 above and 0.005 below. Okay, so 0.5%. And then you would go to the table and you look for that value inside the table to give you your cutoffs. So if I'm looking for the point where 0.005 is below, I could go to my negative side. You scroll through your Z table, find 0.005. Where does that come out? See, it's right between. You see, it's right between negative 2.57 and negative 2.58. You see that on the negative side of the z-table?
Negative what? 2 point what?
Negative 2.57. You see where it jumps from like 0.0049 to 0.0051. And since it's equidistance, remember we average those out. So it's negative. We would average those out to negative 2.575. So that would be the multiplier. So if we want 95% confidence, what we do is we just adjust the multiplier in the confidence interval formula. And if you look back here, they give you the same number, right? If you look at that table for 99% confidence on the other side, it gives you 2.575. I'm looking down at this little summary table right here. Okay. So so the general idea here is that you load up all your confidence level into the middle of the normal distribution, then you take your alpha level and you split it in half. And that goes into the tails. Okay? And so these cutoffs, this cutoff is like that Z alpha notation, but it's actually the alpha level gets cut in half because it's equally split between the two tails. So we call this number, this multiplier right here, is called Z alpha over 2 because it's literally the Z score when you take the confidence level, calculate the alpha level, and split it in half. And so that's how much is above. And then the negative on the opposite side. So the general confidence interval formula, is p hat plus or minus, it's just a Z multiplier times that standard deviation piece, and then that Z value just gets swapped out depending on the types of confidence levels that you want to work with. And there are some common ones. The most common are right here in the list. So the most common that you'll run into are 90% confidence, 95% confidence, and 99% confidence. So you got your confidence level, and then the alpha level associated with that, that's either like a 10% alpha, a 5% alpha, or a 1% alpha. Those are the most common. And then you can see in this table on the positive side, it gives you the Z multipliers. So you see the 1.96 for 95% confidence. You see the 2.575 we just calculated. If you want to do 90% confidence, it's 1.645. And that comes from the table, but I'm not going to calculate that one specifically. Okay? So if we want to up or lower our confidence, all we have to do is swap out that one value in the formula. That's it. Okay? Questions so far? Question?
Yeah, I guess, so basically what you're just saying is like you want to switch out the confidence level.
Yeah.
You just find the new instead of like 1.96 right?
Yeah.
That's just it?
That's it.
Okay.
Yeah. And so, that's why in the table, and typically these are the only 3 confidence levels that most people would ever use.
Okay.
It's very uncommon to see other levels of confidence in statistics. And so that's why those are tabled. You could do it if you wanted. Like, if you wanted to construct like an 82% confidence level, you could do it if you really wanted to. It wouldn't be that hard. You put 82% of a normal distribution, in the middle. So that would leave. So if 82%, what would your alpha level be? It'd be 18%. So you split that in half. So you'd have 9% below and 9% above. And then you'd go to your table and you'd look for 0.09 inside the table. And it looks like the closest you can get to that is like negative 1.34. And so then you could just swap out 1.96 for 1.34, and that would be an 82% confidence interval. Why you would ever want to calculate an 82% confidence level is beyond me, but you could do it. Yeah. Now, standard, just so you know, when you see margin of error reported, like in an article or like a news report or something, the standard is 95% confidence, so there's a good chance they're reporting you a margin of error from a 95% confidence interval. That's kind of the standard.
Is it just because between those two values that are the most common?
Yeah, pretty much. I don't know. 5% just seems like a good error rate, I guess. I don't know. Yeah. But the problem is that if there's a trade-off always between confidence and interval width and sample size. So yeah, 95% is sort of just the standard. But There's no reason it has to be 95%. It just kind of is. Okay. So like here, if we go back to the one we had calculated yesterday, let's suppose instead we wanted to use a 99% confidence interval. What's the only thing that's going to change? Yeah, so the p-hat will still be the same. I can't remember what was it yesterday, 4 or something?
4233.
4233?
Yeah.
Okay, so the p-hat, the sample proportion isn't going to change. What is going to change is our z multiplier. So I'll write down the formula here first. So this is the general formula. Notice I'm not writing the 1.96 anymore. I'm just writing the z value. Then we'll fill that in. So the p-hat's still the same. What changes is now I'm going to go to my table. I'm going to pull out the 99% multiplier, which is the one we just calculated, which is 2.575. And then everything else stays exactly the same as the calculation we did yesterday, right? So it looks almost identical to yesterday's problem. I'm just swapping out. Now I'm going to have, I'll have a higher confidence level. But what's going to happen to our margin of error now from yesterday? Because yesterday, because in yesterday's example, we got this because we took 0.4233 and we did plus or minus 0.05. What was it? What was the margin of error yesterday's? What did that come out to be on yesterday's example? Somebody got that?
0.4792.
Well, before we did the actual subtraction, what was the number we added and subtracted? It was like 0.05 something something.
Oh, 0.559.
559, right? So this was, I'm going to just say MOE because that's how a lot of times you'll see it abbreviated, margin of error. So yesterday our margin of error was like 5%. If we calculate this one though, and what do you get? It should be bigger.
I got. Wait, like
The whole
the
thing.
whole thing,
The
right?
whole thing, yeah.
I got 0.0735.
0735?
I got that too.
0735. Yeah, that sounds reasonable. Okay. So this is our margin of error. Excuse me. See, so our margin of error here is like 7.35%, whereas with 95% confidence, it was 5.59%. What happened to our margin of error? It got bigger. Why did it have to get bigger? We wanted more confidence, yeah. Because if you want to be more confident and you still have the same data, you don't really have any choice except for to give yourself more room for error. That's all you can do. So our margin of error goes up. So in exchange, what's going to happen to our interval? Yeah, it's going to widen. So we're going to go from 0.4233 down that much, and then we'll go up that much. And then what are our two boundaries then in this one?
0.3498
Mm-hmm.
through 0.4968.
4968. Yeah. And that's in comparison to before it was 0. What was it? 3674 up to 0.4792. Right? And it was 5.59% with 95% confidence. So the margin of error goes up because your confidence increased, so your interval gets wider as your confidence goes up. Yeah? What questions do you have about this one? Any of the calculations or numbers that we just came up with? Actually, I didn't come up with them. You guys did. So plausible deniability on my part. No, I'm just kidding. Okay. So if you were going to interpret this, yesterday I kind of showed you how to make a nice interpretation of a confidence interval. So first thing you should state is what?
We're 99%
Yeah, you want to tell people what confidence level you use. So we're 99% confident. Then we should tell people what? You want to tell people what you were estimating. So you tell people what level of confidence you were using, and then you tell people what you were trying to estimate, because we were looking at the true proportion interested in paying for a permit. And then you can report your bounds is between, and then it would be this case. A lot of times we'll switch them back to percentages just because people understand those really well. So we'd say something like that. So, typically speaking, you pick your confidence level in advance, though. It's not something you would normally alter after the fact. You just pick whatever you're going to use before you do your study, and then you go with it in general. So. Okay. So if you up your confidence, you're going to end up with a wider confidence interval unless what happens? What could you do? This is what we talked about at the end of yesterday. You have some control because you could do what?
Increase your sample size.
You could take more samples, right? So what happens if you take more samples? We would think that the interval would do what?
It'd be closer to the true.
Yeah, it'd be closer. So let's say instead, that's one word, not two. So suppose instead it was 600 CBC students and 254 said they'd potentially be. So let's basically assume it's like double the sample size, right? Let's say you would have taken 600 people instead of just 300. Okay. Now, in this case, I did this intentionally, but what happened to the p hat here? 254 out of 600? Yeah, it doesn't actually change. I did it on purpose, but it's just doubled. It's basically the same result from twice the sample size. Okay. So if I were going to go back and recalculate my 99% confidence interval, what's the only thing that's going to change? Just the sample size, right? So we would still use 2.575 as our multiplier because I'm doing 99% confidence. And the p hat didn't change. I did that on purpose. I wanted it to stay the same. The only thing that changed here was I was saying, what would happen if it was actually that result came from a sample twice the size? Okay. Well, calculate our new margin of error here and tell me what you get. So it's all that junk together. .0 something.
0.0519.
0.0519. 0519. Anybody has something different or the same? 0519.
I think I might have done it.
I think I did it wrong.
I think that sounds reasonable. It's about what I was expecting. You did the same thing, Shadi? Okay. 0519. Yeah. Okay, so this is our margin. So in this case, what happened to our margin of error from the example before is gone down, right? So in the last slide, our margin of error was 7.35%. We were giving ourselves basically a 7% margin of error. But with the increased sample size, we were able to knock that margin of error down to like 5%. So we've cut our margin of error of like 2%. We had to double our sample size to do it, but we did it. Okay, and so then so to get the interval right, it would just be 4233 minus 0.0519, and then 0.4233 plus 0.0519, and then whatever those come out to be, I don't know, 0.37 something, 3714, and up to 0.4752. There you go. So we were able to get ourselves a narrower interval because we have a lower margin of error. And the reason is because we took a bigger sample size. Question?
Now, why is it 519?
Maybe did I get rounded wrong?
Because the decimal is 0.5183.
Oh. Did you round somewhere in between? Did you do it all in one big calculation?
You got 1 9, right?
Oh, wait. I didn't put 2575. I forgot the 5.
Okay. Yeah, there you go. That's just, it sounds to me like it's probably just a rounding, just missing like 1,000th or 10,000th somewhere. So, okay. Any questions on that? You feel like you can at least use the formula? Okay. So you want to be able to use the formula. Plus, now we can see the relationship between confidence levels and interval widths and margins of error. Okay. So basically, the idea is, if you want more confidence, essentially what you're going to have to accept is you're going to have to accept a higher margin of error, and you're going to have to accept wider intervals. That's the idea. But you can control it a little bit. What you could do is, if you want to take more samples, then that'll work against the confidence by giving you lower margins of error and narrower intervals. Yeah? Okay. So then, that begs the question, well, I think it begs the question, what question arises from this? Anybody? Like, we just saw that we could decrease our margin of error from like 7% down to 5% just by increasing the sample size. So what if that's not good enough, right? What if a 5% margin of error is not good enough for you? How many should you take, though? See, that's kind of the question that I think comes next. It's like, okay, I understand that I can reduce my margin of error by taking more samples, but then how many to take? Because like, how come when I added 300 samples, or how come when I doubled my sample size, my margin of error just only went down like 2%? Well, I doubled the sample. How come the margin of error didn't half or something, right? Has to do with the square root. But so then the question becomes, okay, well, what if you have a margin of error in mind? Like, what if 5% is not good enough? What if I want my margin of error to be 3% or 2%, right? Well, then how many samples would you have to take? Okay, a lot is the answer. But we can actually figure it out. We can do better than that. We can actually figure out how many samples we should take to get a desired margin of error. So if you think about the formula for the confidence intervals, right? And this chunk right here, this is what we call the margin of error. So I'll just call it MOE, right? Now, so then the margin of error is equal to that z value. Whoops, got ahead of myself. It's equal to the z value times the square root of, p hat times 1 minus p hat all over n. Okay. So could we take that equation up there and solve for n? Can we solve for n in that equation? Well, just in general, yeah, right. Like if we have a margin of error in mind, right? Yeah. We could solve for n, right? Like for example, we could get this z out of the right-hand side. How? We just divide it, right? So we could divide both sides by z alpha over 2, and then we'd have the square root. You don't have to write all this down, but you can if you want. We'd want to get that square root out of there because n is trapped under square root. So what could we do? We could square both sides, right? And then we'd end up with p hat times 1 minus p hat all over n. And then what would we want to do? We'd want to probably multiply that n to the other side. In fact, we could really just cross multiply here. We'll send n up to that side and send that term to their side. And so what you'd end up with is you'd end up with n equals p hat times 1 minus p hat. Dividing by a fraction, though, is the same as multiplying by the reciprocal. So we could just write it this way. So when you divide by that MOE over Z alpha over 2, it'll come to the other side as the reciprocal. And so this is actually a formula we could use to calculate a margin of error if we knew, or a sample size if we knew the margin of error we wanted. That's the idea. Okay? So if we have some estimate of the sample proportion, we know what confidence level we're using, that would tell us our Z value, and we know the margin of error we're trying to obtain, we could actually come up with a sample size number that would tell us how to get to that margin of error. That's the point of the formula. Now, the formula, though, I mentioned here, there's an important note here because this requires some estimate of the p hat, like the p hat's built into it. So this formula will work like if you have a preliminary sample, like if you've already taken a small sample and you have an idea what the p hat's going to be, then you could use this formula to figure out how many more samples you need to get your margin of error down where you need it to be. But you don't necessarily have to have prior information. So I'll rewrite that one in a second. Oops, I actually want to go pen. So if you have, when I say prior information or no, it's basically, do you have an estimate of p hat? Because if you do, then you can just use that formula. But it turns out you don't have to worry about that necessarily. Because here's the thing. About this quantity right here. See, proportions have to be between 0 and what? They have to be between 0 and 1. So it turns out, like, you could graph it. So, like, if you look, so p hat has to be somewhere between 0 and 1. This right here, if you look at that function p hat times 1 minus p hat, it's actually, if you distribute that, it's actually a quadratic equation. I don't know when the last time you guys did quadratics was. I'm sure it was great fun whenever you did it last. But the point of a quadratic is the quadratic is shaped like kind of like a bowl. It either opens up or it opens down. This is a quadratic that opens down, which means it actually has, and quadratics have a vertex, like a maximum value. So if you graph this thing, it would look something like that. And what you'd find out was that this thing maxes out when p hat is 50%. So the most amount of variability you can have when you're sampling for proportions is when you have a 50-50 split. So that margin of error is going to max out at a population with a 50-50 split. So then what we can do is we can just use that as a maximum. So this right here, this will also max out at p hat equals 50%. So if we don't know what the proportion is going to be, like we don't have a preliminary sample, we could just go like worst case scenario. And then we'll say, okay, well, the worst case scenario is we're dealing with a 50-50 population. And so we can just plug that in to the formula. And then, well, what's 1 minus 50%? It's just 50%. And then 0.5 times 0.5 is just 0.25. So you can use this formula if you need to in order to, if you don't have any prior estimates. So there's basically two formulas. That's the point.
Are we going to need this for the test?
Yes. Well, you'll need the formulas and when to use which one. Okay. So there's two potential formulas, and the question prior information or not is this is if you have a p-hat estimate. So if p-hat estimate is available, which may be the case, but if you don't have any estimate of the proportion available, then you can just always fall back on like the sort of the conservative or the worst case scenario sample size calculation. Okay, I'm going to show you how to use both. I'll distinguish between the two. So basically, we now have three formulas. Okay, there's a confidence interval formula, and then you have two options for doing sample size calculations, and it just depends on what information you have. All right, I'm going to show you how to use both of them, though. Okay. So, let's say you're just walking into a question blind. Like, so in this case, I'm walking into a question. All I'm saying is, okay, let's say your job is you're going to go out and you're going to use a 90% confidence interval to determine what percentage of students at CVC work full-time. How many samples would you need to take to get your margin of error down to 4%? Let's say that was your goal. Okay. So in this case, there's no info about p-hat, right? So we're going to have to use, if you're just walking into a study blind with no idea what to expect, that's when you would use that second formula I just wrote down. It's the formula without any prior information. So now, there's really only two things involved here. There's a z-score, and then there's a margin of error. But how do you know what that z-score has to be? Because we know the confidence interval that we're going to construct. So since we know the confidence level, that's something, the confidence level should always be picked in advance of a study. So since you already know what confidence level you're going to pick, you just use the 90% z multiplier, right? So the z value we would use, it comes straight off the table. It would be 1.645, and it's because we would be using, we're going to ultimately use a 90% confidence interval. And then what's the margin of error we're trying to get down to? Well, it tells you right there. It's 4%. But we always use it in, it should always be a proportion or decimal form. Okay. So then essentially, we'll just do 0.25. It'll be, the z value is 1.645. We'll divide by 0.04, and then we'll square it. And then that will get us a number. And what does that come out to? Someone want to try that for me? Say that again. Okay, so it's like 422.82 ... whatever. Obviously you can't take a decimal sample, so what should you do? Round it, and in general, it's always better to be safe than sorry. So for sample sizes, this one happens to be, already rounding up anyways. But in general, we always round up for sample sizes. So it's like the one time that you don't have to follow rounding rules is when you want to be safe. You want to be on the safe side, right? It's kind of like, you guys ever do the math problems where you have to like solve like, how many cans of paint do you have to buy? And then your teacher yells at you because you didn't buy the extra paint can or something. It's like, you always have to round up. It's like that for samples. You guys know what I'm talking about?
Yes.
Yeah. Okay. So, all right. You might as well take one extra person than not have enough. That's the idea. Okay. Any questions about that? So if you're just walking straight into a study, no prior information, don't know what to expect, you can just use this formula as a safeguard. Your margin of error is probably going to come out smaller than 4%. It's probably more than you actually need, but at least you know you have enough. That's the point. Yeah. For what? Well, this one has to be rounded to a whole number because we're talking about samples. We're talking about people. Right? Because like z-scores we round to 2 decimal places. Probabilities I usually go with 4 just to have enough detail in them. But this we're actually talking about like actual people we're going to talk to, so we need to go to whole numbers. Yeah, that's why you always round up to the nearest whole number. Okay. Now, this is not always the case. Sometimes you do have prior information. So I think I have one more example, and then we'll do a sample size calculation with it. Okay. So first we'll do the interval, and then I'll ask you a question about sample size after that. So let's say, for example, they were trying to get an idea about an upcoming bond that was going to be going onto the ballots that people were going to vote for. So whoever was doing the study, they talked to 200 residents. 121 of them were in favor of the bond. And I'd like you to first calculate a 99% confidence interval to estimate what the true proportion of people who are going to vote for it will be, right? Okay. What do we need to do here first? We're doing a confidence interval. It's not a sample size calculation. So I'm going to use my confidence interval formula. But first, what do I need to know?
So is
Diffraction.
Yeah, because I know I'm going to use this formula, but first I need to figure out what my actual proportion is, because that occurs 3 times in the formula, so you better calculate it. So what was the sample proportion in this case? 0. What was it?
605.
0.65, right? Like 65%. Okay.
605.
605. Thank you. Was there a question?
Yeah, where did you get that equation from?
This is the confidence interval formula, right? So I'm not asking for sample size calculation. There's 3 formulas, right? There's 1 formula for calculating confidence intervals. There's 2 formulas for calculating sample sizes. Right now I'm calculating a confidence interval. In a minute we'll do another sample size calculation. Okay. So you have to understand what you're actually being asked to calculate. All right. So this is an interval. Okay. So in our case, in this sample, a little over 60% of people were in favor. Okay. Now the other thing we need to know here is, what's our z-value? What does it have to be? 2.575. Why?
Because we've got 99.
99% confidence, right? And then what's our sample size? Here? 200, right? Okay, so we got everything we need to do the interval calculation. So p hat was 0.605, z is 2.575, the 0.605 goes everywhere else, and then the n is 200. Okay. So let's calculate that margin of error when you get a chance.
Point 0.890.
0.089 something? 0890?
0, yeah.
Yeah, 0.
0.890. Okay. So I'm getting 2 people. Anybody else get that as well? Also got that? Okay, that's 3. So that's pretty good. All right, so then this right here, remember, this is our margin of error. So our margin of error here is basically 8.9%. So the sample size of 200, this is about a 9% margin of error. That's a pretty big margin of error. But anyway, so we can finish this off. So then to get our lower bound, we go from 0.605 down 0.089, and then we go from 0.605 up 0.089, and then what do our boundaries come out to be? 0. What's that? 516?
5166.
516 up to
694.
0.694. Right? So that would be our confidence. You know, you could say something. So, you know, if you were going to interpret that, it'd be something like, you know, we're 99% confident that the true percent in favor, I'm kind of abbreviating here just for space, is between, and then those are our boundaries, 51.6% and 69.4%. Okay. Now that could be, so that might be acceptable. Like say you just care about whether or not you get like 50% approval. So it looks like we're safe on 50% approval, but certain things have to pass with like 60% approval or 2/3. I mean, it depends on the type of vote in the county or the city you live in or whatever. So let's say, for example, maybe you go out and you did this study, right, and you get your initial sample of 200, but you decide, okay, that margin of error is too high, and I'd like to reduce my margin of error. Okay. First off, any questions about this example before I go to the next slide that I want to do? Okay, so let's say that you want to go back out and you say, all right, I'm happy with these results, but I'd like to take more samples to reduce that margin of error. And let's say that we wanted to reduce our margin of error maybe down to 5%, right? So let's suppose you're going to go out, you'd like to redo the sample, you'd like to keep the 99% confidence level, but you'd like to reduce your margin of error 5%, but you assume that the results of that first 200 samples are relatively reasonable. See, so it's like you don't need to act blind if you're not blind, because you have some reasonable estimate of what you think the true proportion is. I think it's around 16.5%. Okay, so if you have this prior information, that's when you would use that other sample size calculation formula that I gave you. Okay, now, so we're going to take advantage of the preliminary sample that was done, and we'll calculate our sample size using that. So in this case, what z-value are we using? Yeah, we're same one we used for the interval because we want to retain that 99% confidence level. And then what's the margin of error we're trying to get ourselves down to? 0.05, yeah. All right. So now I'll say this will be 0.605 times 1 minus 0.605 times 2.575 divided by 0.05 squared. So take a minute and see if you could pull a number out of that. What's that? Yeah, right. So I'm trying to find n.
So wait, how did you get the p-hat?
So it says right here, the very last part, if you assume the result of the initial 200-person sample is reasonable. So that's coming from the one we just did. So it's like you went, yeah.
If you give us something,
Yeah.
you'll give us both questions.
Yeah, exactly. So it's like, hey, you already did some work, so don't like throw it away and pretend like you didn't do anything. You know, you have a reasonable estimate for p hat, so let's use it. What do you come up with if you calculate that?
634.
630 something?
634.
630, what is the decimal?
633.82.
82 ... But again, we always round up, so that's why the answer would indeed be 634. Okay. So then what you would do is you say, well, then basically I just need to make sure that I have a total sample size of 634 people. If the first 200 were collected as a simple random sample, you could use them as part of it. You just have to go collect an additional 434. That'd be fine if you still have that data. Okay. All right. So it's two different types of problems, right? It's like you can create confidence intervals. There's only one formula for that.
That'll say calculate.
Yeah, calculate a confidence interval or use a confidence interval, right? That's the confidence interval formula.
Gives you the-
Yeah, but here, exactly, the question is how many samples, right? How many samples? We're doing a sample size calculation. Same with right here. How many samples is a sample size calculation problem. The difference between these two is that in this one, yeah, we have some information going into it that we can use. We have that p hat from our preliminary study, whereas this one, I don't know anything about what percentage of students work full-time. I'm going in blind, so I'll just use that sort of conservative formula, and then it'll give me a reasonable place to start. It's 423 is probably too big for that. We probably don't actually need that many, but since we don't know, we might as well have more than we need than not enough. So, okay. It's pretty much just three formulas so far. That's all we got. Any questions about that? All right. Ooh. Do we want to go there? I don't actually want to go there. We have to use, when we get to means, it turns out we're going to have to pull out a different table. So I don't have them with me today. So we'll just stop there, and this will be all about proportions. Yeah. Yeah, I'm going to bring it on Monday. Yeah, I got a whole module I'm building for you guys to be looking at while I'm gone. And in that, I'm going to get you the details, and I'll bring everything in on Monday. And I'll let you guys know what's going on.
Yeah, I agree.